Exercise 21b, the definite integral. Last video I was saying, was there a way that we can definitely find the area under the curve? And we use some approximates using rectangles. But I wonder if we could get a more accurate answer. Well, I suppose theoretically we can take those rectangles and make them smaller, and that way you have many more of them underneath, or we can use smaller trapeziums, whatever the case might be. Let's just start with rectangles because it's a little bit easier to visualize. So beforehand we were doing something like this, where we're using a left-handed approximation and we're just doing steps of one, or changes of one. Well, if I made those changes smaller, you'll notice that they tend to fit nearer to the curve. So then my question is, what if I made those rectangles infinitesimally small? In other words, what would happen if the change in x approached zero? You could almost say, if the limit as the change in x approaches zero. Where have we used limits before? But of course in derivatives. And I know that we refer to the thing as the sum of. Well, funny enough, yes, that sigma symbol can transform and turn into the integral symbol. In other words, if I add up all of the lengths, in other words, for every possible x I've substituted into the original equation, times by the same change in x, then I get the antiderivative of f of x dx, which is antidifferentiation. So another way you could look at it is that you can imagine dx as all the little slices of rectangles as we move along. So we can use antidifferentiation to solve for the area. Of course, curves can go on forever, and can we necessarily find the antiderivative for something that goes on for eternity? Well, not really. That would take a very, very, very long time. Or we could just say an infinite size. So what we do is we just usually we'll only find a area of a certain section, otherwise known as a definite integral, by setting a lower limit and an upper limit. And what we do is we put those lower limits and upper limits on the little integration symbol. So if we want whatever the largest number is, we pop that at the top, and whatever the lowest number is, we plop it at the bottom. So therefore, we can find out what the antiderivative is by using these limits. So how does it work calculated? We do the antiderivative of the original equation. We substitute whatever the top number is in for x, and we minus it by substituting the a into the antidifferentiation. You'll notice here, if I've got an original function f, the antiderivative is a capital F. So just so you don't get confused by all these f's. So what does that look like visually? Well, what it looks like is if I want to find an antiderivative of just say this section here, what I need to do is I need to go and find the antiderivative of that entire section, take away that little section there, and that will find us the antiderivative of the one in between. Example 1, evaluate the antiderivative of the definite integral x squared dx in between 1 and 2. So in other words, this section here. So what we're going to have to do is we're going to have to find an antiderivative and then do some substitutions. So let's have a look at the process. So the first thing I would write is I'd write the antiderivative. As you can see here, you'll notice that I've still included the plus c. I'll also explain in a minute how you can finally drop that off because we do a definite integral, and we'll talk more about that in a minute. But I've put little square brackets and I've put a 2 and the 1 there. So what that means now is I now just need to substitute the integrand, if you like, or the integral with x equals 2, and then subtract it when x equals 1. And I'll show you what I mean. So we now have the answer of 7/3. Notice here that when I did the antidifferentiation here, the plus c of the first one that I did, and I subtracted the other plus c, well, they ended up cancelling each other out or equaling to 0. So therefore, we do not have to write this anymore. If you're the kind of person who forgets these sorts of things, there's no harm in writing it. However, when you're doing a definite integral, the plus c is not required because they will get deleted anyway. If you found that you ended up with an answer that had a plus c, you're doing something wrong. Example 2. Part of the graph of y equals 1 minus x squared is shown to the right. Find the area of the shaded region. So our limits here that we'll need to do is -1 and 1. And we put in our equation here, and we just need to solve accordingly. Because it says find the area, we better make sure we have units, and the units, if you're not given centimeters or meters or whatever, is always square units. And so the answer is 4/3 square units. As a note here, these sorts of questions where we got lots of minuses and minuses and minuses are very typical exam questions designed to trip you up if you can't do triple minuses and things like that. So always be careful with your working out. Example 3, evaluate 1, 0, x cubed minus x dx and find the enclosed area between the curve of y equals x cubed minus x and when x equals 0 and x equals 1. So we'll need to go and do our antiderivatives as per usual, and then we'll go and solve for this area. So we found our antiderivative here, which is -1/4. And so theoretically, that's also the same answer in part B, except it has a negative. And this is when I'm always asking you to be careful when you see the word area. Areas cannot be negative. We cannot have negative measurements. So therefore, the area would be equal to 1/4 square units.